we will be talking about gases in a different context. We're going to be bringing back pressure of gases, which is a concept that we discussed at the beginning of this chapter. But instead of analyzing the individual pressure of each gas alone, we will see how when gases are in a mixture, how can we analyze their pressures, or more specifically, their partial pressures? Now, partial pressure is simply the pressure of each individual gas in the mixture independent of the other gases in the mixture. Okay, so for example, let's look at this picture down here. And this picture down here, we have in figure A, we have hydrogen gas. We specifically have 0.50 moles of hydrogen gas. And this particular moles exert a pressure of 2.4 atmosphere. And say we have a different container, okay? Note that both have the same volume, same temperature. We're keeping that constant. And here we have helium, 1.25 moles of helium, and this exerts a pressure of 6 atmospheres. So we know that each individual gas has its individual pressure, and which results, of course, from the collision with the walls of the container. Now, say we mix these two gases together, and now it's again same pressure, same temperature. And now note that because the moles are additive, okay, the pressures are also additive. Okay, so I can say that the total pressure is going to be the sum of each individual partial pressure. Now note this 8.4 right here, which is the total, is a representative of the individual or partial pressures of both hydrogen and helium. So in this case, the 2.4 plus the 6.0 will give me the 8.4 atmosphere. Okay, so this individual pressures in the mixture is called the partial pressures. And according to Dalton's law of partial pressures, that the total pressure of in the mixture is going to be the sum of each individual partial pressure. Now, I've noticed that some have trouble understanding the concept of partial pressure. And the closest thing you can think about for partial pressure is it is proportional to the concentration of gas. Now, again, it's not the concentration of gas, but it is directly proportional to the concentration of gas. So you can think about it in a similar way. And just seeing from the pressures of each gas right here. So for ideal gases, we said we will use PV equals to nRT. Okay, if I rearrange this equation right here, therefore P equals to N over V RT, assuming that the temperature is constant, and of course R is a constant. So we can see that pressure or partial pressure is directly proportional to N number of moles of volume. Remember, we had this as a unit of concentration, moles over volume. So this is what I'm saying, thinking about it as the closest thing to a partial pressure of a gas. And when let's just as referring to the example right here, when keeping the volume constant, when we're keeping the temperature constant, we can see that the total pressure right here, right, which is the sum of each individual pressure, and we said we're going to keep these components constant, it can be directly proportional or used to calculate the total number of moles over here. Again, given that the temperature and volume are both constant. Now, how we're going to use this concept in our calculations, this relationship gives rise to, or variation of this relationship can give rise to mole fraction mole fraction is a concentration unit specific, and it can be used for anything. It can be used for a mixture of liquids, it can be used a mixture of gases, so it can be used basically for solutions. But in the context right here we're talking about is gases. And if we can utilize the partial pressure, so I can say that if I have the partial pressure of a component, so say the P total is partial pressure of A plus partial pressure of B plus partial pressure of C, and I want to calculate, right, the mole fraction, okay, of A, I can say that it is the partial pressure of A, knowing the partial pressure of gas A divided by the total partial pressure. And similarly, from what I just said on the previous slide, that the total pressure is directly proportional to the total moles, I can use this relationship. So if I'm provided with the number of moles, I can say it's the number of moles of A divided by the total moles of A. I can use the same relationship with volume, so many variation. And mole fraction, by definition in this case, which is given by this sign right here. Sorry, I forgot the name of this sign, but I can mention it back at the end of the video, is the number of moles of a component divided by the total number of moles of the component. And with this sense, it can be using the moles, the actual moles, or partial pressures. Since I told you, partial pressures are directly proportional to concentration or can be the volume. So really, whatever you're given in the question is what you're going to use. Now, another thing is for mole fraction, if you have, say, three components, gases A, B, and C, the sum of the mole fractions of sorry, I wrote B first. A, B, and C must sum up to 1. And this relationship can make our lives easier when we're talking through calculations and can save us time. All right, and we can use now mole fraction, right? And along with the partial and total pressures and the variation of it to solve a problem. So if I'm having here, and I did mention this before, if I have the partial pressure of A divided by the total, right, to get the mole fraction, which also can be the number of moles of A divided by the total moles, and say I cross multiply this right here and rearrange it, I can get that, and this is right here is the mole fraction. So I can say that if I am given the mole fraction of A and the total pressure, I can solve for the partial pressure of A. So again, so many variation of this problem can be utilized to solve the next problem I'm going to show you in right here. So we have here a gas mixture contains 1.05 grams of nitrogen and 1.35 grams of oxygen in a 1.35 liter container at 15 degrees Celsius. And it wants you to both calculate the mole fraction and the partial pressure of each component in the gas mixture. So let's start with the mole fraction. So the mole fraction, by definition, is the number of moles of the gas divided by the number of moles of the total. Okay, so now in this case, I need to first calculate the number of moles of each gas individually. So let's start with nitrogen. So the number of moles of nitrogen is going to be the mass of nitrogen divided by its molar mass. So 1 mole of N2 divided by the 28.02 grams of nitrogen. You can get this from the periodic table. And we have here 0.03747323334 moles. And let's track our sig figs. We have here 3 sig figs, 4 sig figs. So 3 sig figs. And I'm going to do the same thing for oxygen. So number of moles of oxygen, 1.35 grams of oxygen. In here, 1 mole oxygen, just dividing by the molar mass of the oxygen molecule. And this gives me 0.042187 moles of oxygen. Again, tracking your sig figs is going to be 3 sig figs. Now, I want to first start by, I calculated the moles, and now the third step is I'm going to calculate the mole fraction of nitrogen and oxygen. And here's what I'm going to use: the relationship of all the mole fractions. The sum of all the mole fractions in a gas solution is going to be 1. So if I can calculate 1, I will do 1 minus the mole fraction of the other to get it. You don't need to do everything to save time, especially on a test. And so the mole fraction of nitrogen is 0.03747323334 moles, okay? And divided by, again, that same number, I'm going to copy and paste it right here, okay? Plus, because this is the total, plus the moles of oxygen. And right here, this is going to give me 0.470410349 moles. Okay, and tracking my sig figs, I will have here 3 sig figs as well. All right, now, if I want to calculate the mole fraction of oxygen, is going to be simply 1 minus the 0.470410349, because according to the relationship of the mole fraction, the sum of the mole fraction of nitrogen plus the mole fraction of oxygen equals 1. Okay, and by the way, this one right here is exact. Okay, so infinite sig figs. And in this case, I get 0.529589651 moles of oxygen. Okay, again, 3 sig figs, since I have here 3 sig figs. Now, I have finished calculating the mole fractions. Let me duplicate the slide right here. And because I will need my previous calculations. And let's now calculate the partial pressure of each one. Now, note that I don't have a total pressure, right? And so in this case, I need to calculate the total pressure, okay, using ideal gas equation, which is PV equals to nRT, right? So therefore, P equals to nRT over V. Now, note that the number of moles are going to be the sum of the moles of nitrogen and oxygen. So this is why I kept the previous slide. So we're going to add these two together. And when I add them together, I get 0.079660733 moles. Okay, let me make room for myself here. And I multiply it by the ideal gas constant times, we have the temperature is 15 plus the 273.15, because this is right here, liter atmosphere mole, okay? Divided by the volume is in liters, which is 1.35 liters. And when I track my sig figs right here, I get, from this particular operation, I get 3 sig figs, because 15 has no decimals. And I get here, it's 1.395277749 atmosphere, and this is 3 sig figs. Now, since I calculated, and this is P total. Now, since I calculated the total pressure, I can calculate the partial pressure of each using a combination of the mole fraction, right, and then the total pressure. So In this case, I can say that the partial pressure of N2 is going to be the mole fraction. So I'm going to copy and paste the mole fraction. Okay. And my advice always is to not round until the final answer. It times the 1.39527749, and this gives me 0.656353. 353,093 atmospheres. All right, and it's 3 sig figs, so it's going to be 0.656 atmospheres. And then for the partial pressure of oxygen is going to be the mole fraction of oxygen times the total pressure, which in this case, let me copy and paste it as well, the 0.529 moles. Okay. Times the total pressure, which we have right here. Okay, and this is going to give me 0.73892465661 atmospheres. Again, 3 sig figs. And this is going to give me 0.739 atmospheres. I hope this made sense to you, and I want you to attempt this one on your own to see if you really understood the concept of partial pressure and mole fraction, and see how we can apply it while I work on it. Now, in this problem, we have a 10 mole mixture of hydrogen and nitrogen gas. And you're given the partial pressure of hydrogen. So the partial pressure of hydrogen is 0.325 atmospheres, and that of nitrogen is 0.500 atmospheres. How many moles of hydrogen gas are present? Now, this is a different but similar problem. The first step is I'm going to calculate the total pressure, right? Because I'm giving the partial pressure of each gas. So I'm going to say here it's going to be the partial pressure of hydrogen plus the partial pressure of nitrogen, which is 0.325 plus the 0.500. Another thing is when you are solving these kind of problems, make sure that the units of the partial pressures are going to be the same. If not, just make them one unit. It doesn't matter which one you choose, as long as it fits within the theme of the problem. So 0.825 atmospheres right here. And then I want to calculate the moles of hydrogen gas present. So I can say that the number of moles of hydrogen gas is going to be the partial pressure of hydrogen divided by the total pressure times the total number of moles, right? Because right here, right, this can be similar to the mole fraction, okay, of hydrogen. So in this case, I can say that it's 0.325 divided by 0.825 times the total, which is 10.00. And, oh, I forgot to track my sig figs. So 3 sig figs here. So in this case, 3 sig figs, 3 sig figs, 4 sig figs. My answer should be 3 sig figs. And this should give me 3.939393 moles. And if I have 3 sig figs, this is going to give me 3.94 moles. All right. Now, say it added one part of the problem and said, what is the number of moles of nitrogen? It doesn't mention it here, but just to show you, the number of moles of nitrogen will be 10.00 minus the 3.94 moles, which would give me 6.06 moles of nitrogen gas. Just to show you an example if you were asked. The last part that I want to discuss over here is collecting gas over water. Now, you might have or might have not done this experiment in lab. In case you did not, some gases are collected over water. Like, let me zoom here. So you have here a reaction between zinc And hydrochloric acid, we can write the equation for it up here. So zinc solid plus HCl will give me zinc chloride plus, which is aqueous, plus hydrogen gas. And we can balance the equation right here. And what is the gas that's being collected over here is hydrogen. And you can see it's collected over water. Now, there is one thing. Water in a closed container system, I'm going to zoom in again right here, kind of evaporates and condenses at the same time. And due to this process, this creates a water vapor at the top right here, creates a pressure on the surface of the water called vapor pressure. So really, when you are now collecting the gas over water, there are two partial pressures: the partial pressure of the hydrogen gas collected and the partial pressure caused by the water vapor, caused by the water being trapped in a closed container system. And for this reason, if we want to calculate the partial pressure of a gas, we can say that the total pressure equals to the pressure of the gas itself plus the pressure of the water. Now, another thing to note that the partial pressure of the water is temperature dependent. And this is how to show you depending on the temperature. Okay, and we're going to talk about that in Gen Chem 2. We're going to talk about how does the vapor pressure affect is affected by the temperature and all that stuff. But for now, you need to know that according to the temperature, the partial pressure right here can vary. All right, and you'll be given most probably this information in the question. And then if I rearrange this equation right here, I can say that the partial pressure of the gas equals to the partial pressure, the total pressure minus the partial pressure of the water vapor. And let's see how we can apply this to a problem right here. And in this problem, you're adding a zinc metal to hydrochloric acid, very similar to the experiment that I just showed you. And hydrogen gas is collected over water, and the vapor pressure of the water that you're given at 20 degrees Celsius is 18 torrs. And the volume of hydrogen gas is 1.7 liters, and the total pressure is 0.810 atmospheres. Now it wants you to determine the number of moles of hydrogen gas collected in the sample. And you're also given the balanced chemical equation. So let's see how we will start this problem. So to start this problem, I'm going to write the equation that I just showed you, that the total pressure equals to the pressure of hydrogen, which is the pressure of the gas, plus the pressure of the water vapor. Okay, and I am given right here this information, the total pressure, which is 0.810, and I'm also given the water vapor. Now, note that the pressures are different, and I cannot work in a problem where two units are different. So the easiest thing for me is to convert the partial pressure of the water vapor from torrs to atmosphere. And you'll be given this, this was on your formula sheet. You'll be given this conversion. And right here is going to be 0.02368421053 atmospheres. And since this is 2 sig figs, this is infinite sig figs, we have here 2 sig figs. All right, and with that being said, I can calculate the partial pressure of the hydrogen, which is the total minus the water vapor. And this right here is going to be the 0.810, 3 decimal places, minus the 0.02368421053 atmospheres. All right, and here how many decimal places? Also 3, okay, decimal places. And in this case, I will get an answer of 3 decimal places. So it's going to be 0.786315785 atmospheres. This is the partial pressure of the hydrogen. Now, I need to calculate ultimately, I need to calculate the number of moles of hydrogen. Now, the number of moles of hydrogen right here can be, oh, let me see if I can move to another slide. The number of moles of hydrogen can be calculated using the ideal gas equation, which is PV equals to nRT. Therefore, N equals to PV over RT, right? So therefore, N equals to the pressure, which I calculated. I'm just going to copy and paste. Okay. Right here. And this is 3 sig figs, by the way, times the volume. The volume is already given to me in the question, 1.7 liters, divided by the ideal gas equation, 0.08, ideal gas, the universal gas constant, times the temperature. It's a 20.0 plus a 273.15. And from this operation right here, I should get 4 sig figs. And note that the lowest number of sig figs is 2 right here. Okay, and this is going to give me 4 sig figs. So my final answer should be rounded to 2 sig figs. And therefore, N equals 2, when I solve for it, 0.05567966683 moles of hydrogen. And this is going to give me 0.056 moles of hydrogen. Okay. No, it should be it should be 0.056 since it is just 2 sig